So my name is Phil Bedard. I'm a TME, which stands for Technical Marketing Engineer for Cisco. And I'm mostly focused, I would say, on network architecture, especially as it usually relates to, in SP, most of our devices are XR related. So most of my expertise, I guess, right now is in XR and kind of the service provider portfolio. And really, this session is kind of, I'll say, a high to mid-level overview of segment routing and Evpn and kind of how we put those things together to provide, I'll say, next-generation services, like how we do things with programmability and simplified control planes. You may hear me say the word simplified, about 100 times, because that's really the goal of what we're doing with things like SR and Evpn is to simplify how we're deploying networks, how we're building networks. I always ask the question, how many people have heard of segment routing? Yeah, you're at a Cisco conference. We talk about it nonstop. How many people have deployed segment routing? Like 3-ish people. And that's kind of where we're at today with segment routing. I'll say the interest level that we have, and some of the marketing guys will show kind of slides. Today at Cisco, we have worldwide, I think, over like 160 engagements with SR today. The number of deployed, and even this year, the deployments will probably move from what was about, I'll say 20 last year to probably 80 this year. So it really has widespread adoption as we kind of move on. But this is kind of the quick agenda of what I'll cover today. It really starts with kind of an overview of, segment routing and kind of a couple of different data plane options. Obviously today, most of what I'll talk about is what we call the MPLS data plane, which is reusing kind of the same data plane that we've used for LDP and RSPT and other protocols to carry as the underlying kind of fabric for segment routing. And I'll talk briefly about IPv6 and how that just adds another level of simplification to the network with SR. And that's kind of a little bit of looking at the future of what we're doing with SR. And then, one of the benefits of SR around traffic engineering. So we're going to spend some time on that and some of the more kind of advanced applications and ways that we can control traffic paths using SR. And then, simplification. Like I said, the real story of this is what we call transport simplification. And when I talk about transport, I'm talking about, packet transport for, normally VPN and IP packet services. And then we'll talk about this notion of intent-driven services. It's kind of like how we use more advanced functions in protocols like Evpn to really drive, advanced services, for layer 2 and layer 3 today. We'll kind of look at a little bit at some of the more kind of advanced things we could do. We tie together Evpn and SR into kind of an end-to-end network to support some, I'll say more, like I said, advanced ways of provisioning services and unlocking more flexibility in the network. And then the other key with this and kind of the simplification aspect is using BGP as like a single control plane for all VPN services. Yep, good. And then we'll look at a couple of kind of very simple defined service use cases. Well, how can I apply this? What are the kind of the problems and services people are trying to tackle today and networks they're trying to build, and how can I apply that to these networks? This slide says reminder, and I'll ask another question, as far as unified MPLS, does anyone have that deployed or heard of it? Yeah, many more. So unified MPLS, or you could call it seamless MPLS, I think is more of the wider industry term. Unified MPLS is a bit of a Cisco term. It's really an architecture that's seen pretty widespread adoption over the last 10 or so years. It's a way that I could create very large-scale hierarchical inter-domain networks to carry VPN services end-to-end. And typically, I'm segmenting my network into various different islands. And those islands are using LDP. LDP is traditionally what we've used for intra-domain packet transport for MPLS. That could also be RSPTE in certain networks. But how do I glue that together? Those are typically only intra-domain protocols. So to tie that all together, we have BGP labeled unicast. And that's where I get this notion of a hierarchical label stack that's used end-to-end. So BGP-LU is used to get from this node to this node. And then in between each domain, I'm still relying on that IGP-based or LDP or RSPTE-based intra-domain protocol. So the key is, how can I simplify that? There's a lot of constraints with BGPLU. I can't really do much with those inter-domain paths from a traffic engineering or, say, a low latency or constraint-based aspect. It's fairly dumb. It works, but as I said, it's a fairly uncomplicated way to build those networks, but there's a better way to do that, and we're doing that through SR right now. And here's kind of like the label stack view of what I just talked about. It's a really unified MPLS, and like I said, this was state of the art, even 5, 6 years ago. And this is the way that people were building networks. And really, it started with this, the IGP. The IGP is critical for intra-domain, IP and label transport, but it always required LDP or RSVP. LDP, if I don't need things like fast reroute or traffic engineering, I need RSVTE if I'm doing any kind of fast reroute or I'll say, traffic engineering end-to-end across that path. But it required I have this, BGPLU layer on top to do any kind of inter-domain transport between those islands. And then when we talk about the service layer, things kind of started with LDP-based services. Traditional, I'll say like Martini pseudowires uses LDP signaling. Even if I'm not using LDP as the MPLS transport underneath, I still needed that for signaling. Later on, we got things through like, Capella-based, VPLS, where we're using BGP, and at least BGP signaling to signal those sort of pseudowires end-to-end across the network. But how do we simplify that? And the first kind of iteration at Cisco that we did was really, getting rid of the LDP and RSVP layer and making that IGP based with SR. Because SR directly runs over the IGP. It's not an additional protocol. It's not an additional control plane layer of new protocols. It's just extensions on the existing IGP. And I'll talk more about that in a few slides. And then additionally, eventually we'll get to this design, but I'm going to step through this as we go through the presentation. But this is sort of the end-to-end view that we have. And this is kind of where we were at, I'll say, a year and a half, 2 years ago. Is simply replacing that, IGP domain and the LDP and RSVT with SR. So I don't want to put the cart before the horse there, but really we're going to start with kind of, how we go from like what was that legacy network with BGPLU as the inter-domain transport, or even sometimes with an intra-domain, and get to just this point where we have IGP with SR. How do we eliminate the LDP and RSVT layers of that? How do we do that with SR? How does SR work to do that? So this is kind of I'm not going to read everything on this slide, but really when we look at SR, we approach SR from the point of view of, it's really an architecture. It's not a set of protocols. There are no new protocols with segment routing. Segment routing is really an architecture that utilizes existing extensions or protocols or extensions to existing protocols to solve these needs. So like I said, one key thing, you eliminate one label distribution protocol. It says LDP, it could be RSVT as well. That's really a simple thing to do. You eliminate things around synchronization that's required between those protocols. And another big one is with SR, and I'll talk about this in more detail, you kind of get built-in fast reroute. So if you're looking for 50 millisecond local protection for my traffic, I get that automatically with segment routing. And that happens without loops, without 100% coverage of different topologies for link and node protection. The other part is it was really the architecture was designed with this notion of, I guess, what we call SDN in mind. The idea from the very beginning was I could have a programmatic way to create an end-to-end path across the network that didn't have the state of something like RSVTE, but was more flexible and that was easily extensible in order to add more advanced constraints to that traffic. So I said, you think of SR, definitely think of it as an architecture and not a protocol, because that's really how we think about it. And this is sort of the basic, the very basic beginning slide that we show many times with SR. And the key point of this, and I won't go through all of that, the key point is that in SR, what I want to do with an incoming packet, all of the intent of that is expressed in the packet header on the first node. Unlike, if people are familiar with RSVP or LDP, labels change like every hop within that network, which means there's a lot of state that's carried, end to end across the network. With SR, I can, basically express all of that intent at the very ingress node, and I can express a dynamic path or an explicit path, depending on how I want to compute that path across the network. And like I said, if you look at the data plane, you look at the control plane and this part of it, you can see that there's not really any new protocols there. I'm reusing extensions, or I'm reusing old protocols with new extensions to accomplish what I need with SR. And like I said, the path options are either dynamic, simply shortest path computations, or I can express more intent in that and do things like static paths end-to-end across the network. At the very basis of SR is this notion of a segment. It's called segment routing. And a segment is really just the path I need to take to get to A to Z. And a segment doesn't necessarily have to be one hop. A segment could be multiple hops. In this case with SR, the basic kind of building block is this idea of what I call a prefix segment. And a prefix is really a identifier that's attached to an IP prefix. In this case, I've got this 1.1.1.5/32, and it's using this 16,005 as a prefix identifier. And typically, that's attached to a loopback interface. And that's how I globally identify that node. Another thing to keep in mind with SR and segment routing is all of the, generally with this type of SID, or a node SID as we call it, it has global significance. So it's unique across the entire network. So in the case of this network, I can address this 16,005, or I can basically insert a packet with that one label on it, and it will find that destination. So that's really kind of one segment. Even if it's a multi-hop path that it takes, it's really one segment to reach that destination node. It's kind of one of the beauties of SR is the ability to have those globally unique identifiers to address where I need to go on the network. I would talk too much about this, but the way that we build these SIDs is in the MPLS domain. As far as the MPLS data plane, so I have this thing called a segment routing global block, and that's really kind of a range of addresses that I can use. And then I use an index to add on to that. So it's really built from the sRGB and the index. The reason that they did that from the very beginning was because different vendors use different sRGBs. I would strongly recommend that if you're building an SR-based network to use the same sRGB across the entire network. In some cases, you can't do that for scale. You can't do that. Different vendors have different ranges. So definitely kind of keep track of the indexes you're using. But if it's, say, an all-Cisco network, I would definitely build them with the same sRGB everywhere. And if there's questions at any time, just raise your hand, and I'll be happy to answer anything. But you may ask, that's how I get to a node, but what if I want to use a specific link in segment routing? And that's where we have this notion of an adjacency segment. So an adjacency segment is actually only locally significant. So every node could potentially use the same adjacency segments on all of its links, because it only has local significance to that node. It's still advertised end-to-end throughout the IGP. So in this case, you can use ISIS, you can use OSPF to advertise this information. It all shows up in the database, whether it's an ISIS database or an OSPF database. All of the links, all of the prefix SIDs that are assigned to a node are distributed end-to-end across the entire domain. Again, this is an intra-domain use case. So the assumption is all of these nodes are in the same IGP domain. For local significance, like I said, it still says the sRGB, but there's actually a different, for the adjacency SIDs, we actually use something called that SRLB, which is the segment routing local block. So it gives you a different block to use. And like I said, it's only locally significant. Every node could be allocating the same adjacency SIDs for their own links across the network. I guess I kind of jumped ahead there. So this is sort of the adjacency segment and how I can have a single SID that's attached to that same link. I guess this one is the real key to this one, and I think the key point of this slide was it's ECMP aware. So when I have a path that goes to a node SID like the 16,004, end-to-end across the network, I don't lose ECMP with that. LDP is also ECMP aware. ISIS or SR is very similar. So no matter where that is, if there is an ECMP path to get that to that node SID, it will use ECMP. And it doesn't matter if it's on the ingress node or if it's at a midpoint node. I can use ECMP anywhere across the network. Right, so this is kind of the adjacency segment, and this is kind of how we put together things and how we combine. This is really where traffic steering comes into play, and if I do need to create a explicit path, not only that goes to a certain node, but also it uses a link off of that node. This is how I combine these segments together. So you can see if I want node 1 to go to node 5 and take an explicit path through node 4. I simply just, on the ingress node, I'm creating that label stack, and that's what directs traffic to go to that specific node and that specific segment. And like I said, that's really how, when I say that the traffic intent is expressed on the first node, this is an example of that. So there's no state on node 2 or node 4, apart from it knowing about the node SID and its local adjacency SID to get traffic end-to-end across from 1 to 5. And again, some of the benefits to do something like this with RSBTE, you could do this with RSBTE, but it requires, actual explicit path state at every node across the network, or every node in that path. The labels change at every node in the path. In this case, I don't have any state in the network to do this, and that's where we get the notion of stateless paths end-to-end. Like I said, when we look at this from the data plane, like I mentioned, all of these node SIDs, they have global significance. They're all distributed throughout the IGP. So in this example of going from node 1 to 4, and like I said, this notion of a segment, really is a single segment, because I'm using that one label to address a path end-to-end to the exit node. And normal MPLS data plane operations, at each hop, I'm basically just swapping the same label. So each node knows how to get to this 16,004 label. So the node 2 simply does a swap. 3 in this case is doing a pop because we still support things like PHP or penultimate hop popping with SR, similar to other MPLS data planes like LDP signaling and RSBTE. So we support this notion of, for lack of implicit null, and we also support things like explicit null as well, but we still do PHP with SR. What's that?
What is swapping in this context? Swapping, it's the same label.
It's the same label, but you still have to, when you look at an LFIB and the way the operations work, and he's asking why do I need to do a swap operation? In essence, it's just really the way that internal MPLS data plane works. It knows that if it sees that SID come in, or what we call a SID or an MPLS label come in any interface to that, it still has to do a kind of an internal swap operation. Oh, for it to do the swap? No, I know. In order for it to say, look at the label and keep the same label, it's really internally within the device, it's the same operation as a swap. So if you look at the actual underlying, logic of how that forwarding plane works, if it had to check to see if it was the same or swap it, it's the same operation. So in order for it to make it, as easy for us to implement that in the data plane, it's easier to just treat that as a swap operation. You'll find that with almost every vendor, it's the same. It's really to make it as easy to implement and easy to go to this type of architecture. I definitely understand the point, though. Like I said, it's more of an implementation ease. So we look at the SR segments, and this is kind of just an overview slide of some of the things I've already talked about. When you look at the adjacency segments, the prefix segments, everything is advertised or signaled by OSPF and by the IGP. There's specific OSPF extensions for SR. There's ISIS extensions for SR. And we pretty much, but in XR, we support all the same mechanisms for both OSPF and ISIS. So we typically are not preferring one IGP protocol over the other. I'd say widespread across the industry, there's definitely a lean towards ISIS. It's more popular in SP networks, so a lot of features come to ISIS typically first. But at least for IPv4 SR, what we call MPLS data plane, we try to do both at the same time. So like I said, we took, say, minor extensions because, like I said, there's nothing that new to it. It still interoperates with existing networks, whether they're SR enabled or not. And everything's sort of automatically allocated by the router in the case of the adjacency SIDs. With this, like I said, typically you're assigning just one static SID to a router, and that's to your loopback 0 interface or additional loopback interfaces. That's the globally significant label, and that's really usually all that's important to give you the end-to-end connectivity. And we always show this slide to show how easy it is to basically enable SR, and this is an iOS XR example, but it's not much different than, say, iOS XE. With ISIS, it's really 2 commands to enable SR. Simply turning on the MPLS data plane and then assigning a prefix SID. And like I said, this is the globally significant SID. I'm assigning that to the loopback interface. That's, like I said, that's really all that's needed to enable SR on the node or on the network. OSPF has one more command, but it's not that complicated. So we kind of go back to our, I'll say, journey of simplification. And it kind of shows how I've eliminated LDP from this. I've simply eliminated LDP and particularly RSBT as well. We'll see how we completely eliminate RSBTE. So just enabling SR and node segments and the simple IGP related way of doing it doesn't completely eliminate the need for RSBT for FRR. But I've shown that how you can completely eliminate LDP. And like I said, it's 2 commands really to enable SR potentially, so it's very easy to get it up and running. As long as you're running the right XR version, but we supported SR now for quite some time. So how do I get rid of RSBTE and the functions that RSBTE has? One of the main things people deploy RSBTE for is for fast reroute. So I'm really talking about local protection for links and nodes when failures happen. I want to reroute traffic very quickly and not wait for IGP convergence to happen. So what we have with SR is what we call TILFA, and it really stands for Topology Independent Loop-Free Alternates. It's a long-winded way to say FRR. But the idea and the key concept with this is the concept of loop-free. What it really comes down to is I'm computing what we call the post-convergence path that the traffic's going to take after the IGP converges. So I'm pre-computing what the IGP will look like prior to the failure for that link or for that node, so that I steer traffic to the exact right node so that traffic won't loop. And I've got a few more examples of that coming up. This is a very simplified example of what TLFA does. Normal steady state, I've got traffic from A to Z, and it would take this path through here. My metric on here is it's 1,000. The rest of the metrics are 10. And you can see to back up this interface, I simply just send traffic down this path. There's really nothing special I need to do. I'm using the same Z prefix SID on that packet. And traffic won't loop because this metric is very high. So when it, within the 50 milliseconds, it sends traffic to this node. And there's IGP convergence that's happening. But this node 5, his normal IGP path to get to Z goes through this path. So it's a very easy use case. I'm just shunting traffic onto that backup link. So here's a more complicated example, which may be, I'll say, a bit, and this may be a more typical example where I'm using the same IGP metric everywhere. And it's a classic kind of looping example that doesn't work well with FRR and some other fast reroute technologies. Because now I see if I'm sending traffic from A to Z and I have a link failure here, and I just simply send the traffic to 5 right away, I can see that its shortest path is actually back through 1 in this area. So during that time of reconvergence with the IGP, and IGPs converge pretty fast these days, on a network this size, it's probably 200 milliseconds. But during that time, I'm going to loop traffic back and forth between these 2 nodes, because this guy doesn't know that link has failed yet. He won't know until the IGP reconverges. So what TLFA does is, beforehand, it will actually create or compute a tunnel from A to 4 to protect that, or actually it's from 1 to 4 to protect that path. And it knows once I get to 4, 4's normal IGP path to get to Z will take this path. So that's the notion of computing a post-convergence path to avoid looping happening. Like I said, it's all done on the local node that's doing the protection for that specific link or for that specific path. So when it does that, it adds the node SID for R4, and the prefix SID for Z is already there. So I simply just add one more SID to direct traffic to that node, and then it'll go on to the right path. Here's a bit of a more, I'll say convoluted example, but we do see topologies where occurrences like this do happen. And this is a use case where, I've got a very high metric on, say, this path down here. So I have to find a way to I know that when this link fails, my only path to get to this node is through this, this path right here. But the problem is I have this, 1,000 metric, link in the way. So it's going to direct pretty much all of these nodes are going to send their traffic, back up to here. So that's a problem. That's going to create looping. It's going to create issues that happen. But I have the ability to compute a path that kind of overrides this metric and gets traffic to this node no matter what, because that's my only post-convergence path to stop looping from happening. And I do that by not only applying this R4 node SID, but I also apply the adjacency SID to force traffic on that link. Go ahead. So the adjacency SIDs are all advertised in the IGP. No, so it knows. Yeah, so that's how it knows to use that specific adjacency SID. Yeah, even though they're local to a node, every node in the network, it knows which adjacency SIDs are connected to which node. So it can do things like compute that. Correct, yeah.
And it's now in the router 1?
It is. So all of the local, yeah, they're distributed everywhere, yeah.
From small ISIs database, we have now a lot of additional information.
Oh yeah, you definitely have more information because yeah, you need that to compute, those potential use cases, yeah. Yeah, to be honest, like when you look at the, the TLVs and the size of the TLVs that you have, like, the actual link state database size does not grow too much. And I'll say within XR today in modern devices, we test usually up to around 2,000 nodes in a single domain without really any issues. The CPUs we use in devices today are not quite as crappy as they used to be. Even a pretty low-powered device has a CPU that can do SPF calculations in microseconds today. So it's good.
The other point is that those TLVs are not, those adjacency SIDs are not actually part of SPS.
Oh, they're not. They're not used unless they're actually needed. Right, exactly. So yeah, it's just database entries. And like I said, if you're calculating LFA paths, then potentially you have to use that topology. But normal node-to-node SPF, that's not part of that computation, exactly. So like I said, that's a way that we can do things with TLFA to really protect in almost any situation. And again, enabling TLFA, and this is on a specific interface, but it's as simple as these two commands on the interface enables protection for that interface in TLFA. And we definitely have, ways that we, if we can do just a 0 segment directly connected backup path, that's what we want to do. And then it'll move on to segment, a 1 segment, and then a 2 segment. You'll see in the diagrams, and you'll see here this notion of a P and Q node. And a lot of times you hear about LFA and TLFA, you'll hear about interesting. A P. I thought it was like a pig cell phone, but not quite. You'll hear about P space, you'll hear about Q space, you'll hear about extended P space. It's a really elegant way to define which of those spaces intersect, and to calculate where I need to tunnel traffic to get it on the post-convergence path. but I'll say, it's best for a different discussion. There's also an IETF draft that just covers TLFA, and it has, a number of use cases, and it has a number of many pages of algorithms on how you calculate those. So if you want to, so P and Q space is very important, but I'm not going to dive into that today. So now we've seen how I can basically eliminate RSBT from the network. I'm basically taking its main use case of FRR, and I'm doing that simply by enabling it with the 2 commands with SR on the node, and that's it. So you're eliminating that state completely. Like I said, RSBT, the 2 main use cases for RSBT is both FRR, and the other one is traffic steering. So how do I deal with traffic steering? How do I deal with creating an optimized path end-to-end that's static across the network? The way we do that with SR is this notion of SRTE, or SR traffic engineering. It's as simple as what it sounds like. It's the ability to use SR to steer traffic across an explicit path across the network that satisfies the constraints that I see. We do that through what we call an SR policy. It's a little bit different nomenclature than something like RSBTE, where most things are either called a tunnel or an LSP, label switch path. So we have this idea with an SR policy, and if you really want to keep track of the comparison, you can think of an SR policy as a tunnel, for lack of a better word. Just don't let the SR guys, don't repeat that to them or that I said that, because they'll say it's not a tunnel, it's a policy. Yeah, that's true. This is going on. Anyways, I guess it was fun while it lasted. So basically, like I said, the prefix and adjacency SIDs, those are advertised across the IGP. So every node is capable of creating an SRTE policy between itself and other nodes, satisfying a set of constraints, or satisfying or using even like a static list of labels or a static list of SIDs across the network. Like I said, and again, there's no per flow state in the network. All this is expressed in the first node in the packet header. So I'm simply assigning that one label stack to do this, end-to-end TE. It's the very simple example that I showed before with using the segments. I simply have an SRTE policy on this node that directs traffic to like this node and then out this specific interface on that adjacency SID. So what makes up an SR policy? Like if I'm looking at the configuration on a node, what are the things that constitute an SR policy? And there's 3 unique values that uniquely identify a specific policy. One is the head end. That's simply the node where that policy starts. That's my ingress node for the network. The other is what we call a color. A color is a numerical value that differentiates, I'll say, if you have 2 SR policies that go between the same 2 pair of nodes, or between the same pair of nodes, you have this, the same, head end and destination. A color lets me use multiple policies between those 2 nodes. And each color could be assigned a different constraint. One could be for latency, one could be for bandwidth measurement, one could just be simply the shortest IGP path. And the endpoint, obviously, is the destination node. So we call this like a unique tuple of basically the head end, the color, and the endpoint that define that policy end-to-end across the network. Like I said, it's a little different than, like, say, RSBTE. There I have to kind of create multiple tunnels. I don't have a color there to really differentiate which tunnel is being used for which purpose. So we're using the color to really differentiate and really be used as the identifier for the constraints for that tunnel policy. Like I said, I kind of talked a little bit about this. It's really the treatment. It's the SLA for that specific policy. Only one policy, like I said, it's what really uniquely identifies that specific policy between a set of 2 nodes. So in this case, between this, I have a policy that has these attributes, 1, green, and 4, green being the color. That's uniquely identified versus 1, blue, and 4 on node 1. And in this case, they take 2 completely different paths. The green one, it would be potentially a low latency path, and the blue one could be specified for high bandwidth traffic. So how do I get these paths? Like, I create an SR policy, and I'm talking about static paths or statically defined paths. What are the kind of the mechanisms that I could feed into SRTE to get those paths? And today we support different mechanisms. CLI obviously is one. I could configure an explicit path end-to-end across the network, or I can basically create a policy that also routes traffic dynamically using the IGP or some other type of criteria. BGP is another mechanism. There's actually a mechanism called BGP SRTE where I can define a complete SRTE policy and advertise that via BGP. The node will ingest that BGP NLRI and its new NLRI or new AFI-SAFIs for specific to SR policy. I'll say that one's not quite in such widespread use today, so I probably won't talk much more about it in this presentation. But it's definitely a mechanism to distribute policy information. PSEP is very popular today. For folks not that familiar with PSEP, it's the Path Computation Element Protocol. It's been around for many, many years now in the context of RSVPTE. It's been extended to support SR, and it is a mechanism to instantiate a specific path across the network. And obviously things like netconf. Netconf is really CLI and netconf. You could kind of tie those together. It's really instantiating a static config on the device in order to build my policy. And we have this notion within a policy of this candidate path. So a single policy can actually have multiple candidate paths. So just because my overarching policy with its constraint definitions, under that single policy, I could have different paths, and each path is really kind of what we call a segment list. I said it's really a stack of labels in the MPLS data plane point of view. And I can, I showed this diagram of where I could actually get path information from. Within a single policy, I can actually get candidate path information from all of those sources. I could have one candidate path that's PSEP based. I could have one that's static based. A good example of that is things like fallback. So if I want one candidate path to be PSEP based, I lose the connection to my PCE. I can have a fallback candidate path under the same policy that may still use something like IGP. So it's not just going to go down, it'll fall back to a different path. And by default, when we define a candidate path, it actually load shares traffic across all of those paths. It can use ECMP. They have preferences, so I can prefer one over the other. If they have the same preference and the same what we call weight, then they basically load balance traffic across both of those candidate paths. But you can have different weights. The different weights are used to, what we call like unequal cost load balancing across paths. So if I want 80% of my traffic on one candidate path and 20% on another, I can do that. I configure that today. Like I said, candidate paths can be dynamic or explicit. I could say one candidate path just simply uses the IGP. The other one could be a static SID list across the network end to end. So here's kind of what we look like when we look at, this kind of gets a little lower layer about, what an SR policy looks like. We program it into the forwarding table. And again, here's my SID list. And this is an example of just a single candidate path that's being used end to end. But we have this notion of the best selected path. So we go through a selection process just like BGP. The highest preference is typically chosen as the candidate path. And we have this notion of called a binding SID. And a binding SID is used to represent the best path or the chosen path across the network. We actually utilize this notion of a binding SID to direct traffic into that policy. So a binding SID is really, it's an abstraction for that policy at the MPLS layer. We use that typically, internally within the device if we're doing something like layer 3 VPN. A layer 3 VPN, next hop, if it's pointing to an SR policy, it'll reference the binding SID. And that doesn't change, So if I choose a different candidate path that has a different SID list on it, the binding SID, won't change. It'll just point to a different SID list. And that way we don't have churn when paths change at the upper layer when we're actually steering traffic into the policy. So we keep the binding SID the same. That way, like I said, we don't have a lot of churn at the higher layers when changes occur. There's also some advanced use cases I don't necessarily talk about today where you can use the binding SID and you can reference the binding SID in another SID list. And it lets you do more advanced things like build hierarchical SR policies that utilize binding SIDs end to end across the network. Like I said, it gets into some more advanced kind of traffic engineering use cases that I won't talk about today, but there's definitely deeper dive SR sessions that will get into those concepts.
Does that actually get around
Absolutely. So yeah, we definitely have a notion of a hierarchical policy, where you may have, internally we call it a transit SR policy that's used to transit a defined domain like a core network. And then I reference that binding SID, and I can basically use, 2 SIDs instead of maybe 7. Exactly. Yeah, I don't talk anything about like maximum SID depth. Go ahead.
So that binding SID then must be something that's actually advertised in the domain for that to be able to be used?
Not today. The idea is that we will do that, going forward. Today, because really like an SR, it's not a link, it's not a loopback interface, so it's sort of this ephemeral thing. The idea is that we'll advertise, those up to like what we call the PCE, but they won't be advertised end-to-end across the network. The binding SID is, could be used in a number of different ways, and you can even use the binding SID attached to like an RSVTE tunnel to do sort of inter-domain, and if you've got an internal domain that's RSVTE based, you can assign a binding SID and then use that as an end-to-end SR point. This is sort of an example. It kind of covers all the kind of topics I talked about, but it is a weighted, ECMP example. So this is a case where I'm doing unequal cost load balancing. So I simply have like 2 SID lists, and the SID lists are defined outside of the actual policy, just so you can reuse them potentially. So I've got one that's taking this explicit path across the network. This one right here would basically be a adjacency SID. And 2, just simply references an IP address. And with our SR implementation, the node SIDs, what we call the prefix SIDs that are attached to a loopback, you can actually specify an IP address in the list, and it'll translate into the actual SID. We have a database of every IP in which SID that it attaches to, so you can build a list using either or. If it's a bit more readable to build in with a v4 address versus an actual MPLS label, but you can do either one. In this case, like I said, this one here, I've got a weight of 1. That one I've got a weight of 4. So it's basically, this one will take, in this use case, 20% of the traffic. This will take 80% of the traffic end-to-end across the network. It's animated. Anyways, you can see end-to-end, that's the way I take the paths across the network. And yeah, when we look at the fib on that, my incoming label is simply 1000. And that is the only label that's, I said, I can explicitly set this binding SID, or I can let it be dynamic. In this case, I'm explicitly setting the binding SID. So I can definitely, if I know about that binding SID, like I said, it's not advertised today across the network. If I know about it, though, and it's explicit, I can use it. So I could definitely reference this on another node as a hop across the network, and it will expand it to this SID list. So that's a bit about what the data plane looks like on the Ingress side, and on this side, and I said 20 to 80%. I say these are percentage weights. I think they go 0 to 100, so you can kind of set them to what you need to weight the traffic. So I said, with those additions, with SRTE and the ability to create paths kind of dynamically and statically that are engineered across the network, I've really eliminated, all the benefits that I used to get with RSVTE. So that's kind of how we simplify the stack even more. And as you can see, I'm doing all of that just with the IGP with SR extensions. Go ahead. Is there an equivalent or a shared risk link groups? There are. So I didn't go through the different constraints that you have when you create the path. The ones that, that we have implemented today are like disjoint paths. We have this notion of, associations of SR policies. If they share the same association, we can make them disjoint. We also have affinities, which is admin groups similar to RSVTE, but we also have SRLGs as well. So there's SRLG support. The other ones that we support is like latency today. We can do latency a couple different ways, but I'll talk a little bit more about that when I get to kind of more advanced topics. Like you see, we've replaced what we've done with RSVT in the past with SR completely. And as we would say, it's basically simple and efficient transport of services on top of MPLS. Like I said, this is the MPLS data plane that I'm using. Very simple example of a layer 3 VPN. So we basically, steer traffic into that, SR policy. Like I said, you don't need an SR policy defined to use SR end-to-end across the network. You can simply turn it on and it replaces all of your previous label distribution within a single domain. I said you don't need policies to do that. You need policies to steer traffic explicitly. So we talk about like how do you migrate? Most networks, I can't just, I'll say, turn off what I'm using today and then, turn on SR and have everything happen. There's very few greenfield networks that are built today. Almost everything is what we consider kind of a brownfield network. So we kind of take a look at an example of a network that's, potentially using both LDP and SR, and they work differently. As you can see with SR, I'm basically, this is the same label in as same label out. Whether it's swap or keeping it the same, it's using the same label end to end. LDP, does not do that. The label distribution mode of LDP changes the label at every hop. So I need to do a swap at every hop for LDP. And this really kind of is an example of like an inbound, IP or MPLS packet that's coming into these two protocols. So how do I potentially, run both of them at the same time? That's usually the first step is, can I turn on SR while LDP is still running? And the answer is absolutely, you can turn it on at the same time. It's really kind of what we call the ships in the night approach. And like I said, to enable SR, I just simply turn on segment routing MPLS. But then I also have this other knob called segment routing MPLS SR prefer. Without that turned on, if I have a LDP FEC that matches my SR, say, node SID to this 1.1.1.5, it will prefer the LDP path. It assumes LDP is what's configured end-to-end across the network, so it'll use that by default. You turn on this command, it'll start preferring SR. So it allows you to kind of run them ships in the night. I can migrate nodes to SR, and then finally, when things are fully migrated, I can start preferring SR over that before I turn off LDP. We also have this notion of what we call a SR and LDP interworking. So the ships in the night and migration, it may not be enough to like fully use SR and LDP. There's a lot of legacy gear out there that runs LDP that may never run SR. That's just a reality of what we've seen with lots of customers. Is LDP islands that gear is not going to run SR. They'd like to go to SR. So this is really kind of many, even almost from the inception of SR, we did a way to do interworking between the two. We use this notion, and I won't go into it in too much deetail. We use this notion of like what we call an SRMS or a segment routing mapping server. It simply uses an interworking function between the SR and LDP domain to take the LDP FECs that are being advertised and translate those into advertisements for SR. So it translates those LDP FECs into the OSPF and ISPF extensions to advertise that prefix into the SR domain. So if I'm in a pure SR domain, I now have a path to get to an LDP-based destination. We don't really do it in the opposite direction. We do it from SR to LDP. We automatically advertise those SR bindings or those SR prefix SIDs into LDP. So we don't really need the same mapping function. And we decided to make it so that it's somewhat configurable so that I don't translate every single LDP FEC to the SR domain, just the ones that I need. Then you just simply make the range as much as you need. So, yeah, you could. Yeah, it could match. And this range here is basically like it's specifying where those SIDs start. So you see kind of an example here. The index will increment based off of that number, that range. So I just simply set the base prefix and what I want to match and the number that I need in there. That's my base. So when you talk about the base now is 400 and not 0, or not 10, basically. So what I have is an index. The range specifies the index. The 400 is where I want to start. So like I said, I talked about the sRGB, the global block. Like this allows me to basically specify a different starting global block that's different from my dynamic or my other. It basically separates the domains. It lets me pick and choose which ones are native SR assigned and which ones are kind of LDP to SR auto assigned. Well, I said, this is very simple. It's kind of just a summary of, kind of what I talked about before, and being able to simply enable it in ISIS or OSPF and turning on that knob and kind of the ships in the night configuration. This kind of just gives an example of the LDP to SR inner working. Like I said, it's not dynamic. It requires this node 3 really know how to use that inner working function. So it knows that when it gets an inbound label, based on this FEC, okay. It's more animated than I thought it was. But anyways, it copies this SR label that is associated in the SR domain to that prefix into this, I'll say, inner working function. So then when it has the incoming LDP label of 9007, it knows to automatically translate that to the node SID. And it does something similar on the way that I go from SR to LDP. So here I'm starting with SR, and I'm going to an LDP domain. It needs to, the inner working function, knows to copy that outbound LDP FEC label to the SR database, or LFIB. So that kind of covers, some things, what we call, there's a lot of slides that cover kind of intra-domain transport and intra-domain, paths and intra-domain migration between existing protocols. And I'll say, between RSVTE and SR, there is a good migration. RSVT is a tunnel type mechanism. The best method we have for things like migration is using those binding SIDs. It doesn't work the same way as LDP. There's no analogous way to tie those things together. But you can absolutely run RSVT and SRTE at the same time. There's no limitations with any of that. So we talk about inter-domain transport. Like I said, we've talked about the notion of how we build things when everything's in the same domain, the same IGP domain. So what happens when I've got multiple domains? And as I referenced before, that's kind of the domain of BGPLU. BGPLU is how I tie together different domains and get end-to-end MPLS transport against those domains or across those domains. But here's kind of a simple example of how networks could potentially be built. I could have an access domain, a core, and an access, or I could have multiple domains. In this case, I've got 5 end-to-end that separate different parts of the network. We definitely see networks that are, I'll say, larger networks that are built this way, where these domains are typically, not the same ISIS domain or OSPF domain. These may be completely separate domains, or this may be a separate L2. This is an L2 and L2, and that's a level 1 domain. But we get the flexibility of how we build those networks, and SR definitely gives us more of that flexibility in a simplified way versus BGPLU. So I said, this kind of goes back to the stack that we had referenced from the very beginning of what this stack looks like. And like I said, eventually our goal is to get to just the IGP with SR. And this is sort of the evolution on how we get there for inter-domain paths. So basically, how can I replace BGPLU and why? The why I kind of alluded to, it gives you, you can't do a lot of constraint-based paths and things like that with BGPLU. BGPLU is fairly dumb as far as, it gives you end-to-end MPLS transport, but not a lot of intelligence above that. Yeah, like I said, here's kind of the reminder of the BGPLU-based design, where I have, what I call an inter-domain LSP, and then BGPLU is my inter-domain LSP. So the goal is to, basically eliminate that from the network completely by using SR. Like I said, our first evolution of our designs, which is really EPN 5.0, and EPN is a validated design. We come up with different EPN designs. It's kind of migrated to a different name today. The name of it is the Converged SDN Transport. But which you think of as maybe EPN 6.0. But 5 simply replaced LDP with SR. So how do we go above that? How do we just eliminate BGPLU altogether as well? And one thing that I didn't talk about in sort of the basic SR things, because it doesn't really have a lot of applicability until you look at it has more applicability in the notion of interdomain, is this idea of an Anycast prefix segment. And you can really think about it the same as you think of an Anycast IP on a set of hosts. It's really assigning the same IP address and the same node SID to a pair of nodes And it doesn't have to be a pair of nodes. It could be 8 nodes, as many as you want. And the notion of that is it allows me to create what I consider a redundant border between these domains. So these are domains that are not attached. They're not in the same IGP domain at all. But if I assign the same SIDs to these 2 nodes, I can reference that one SID at any point along the network and use those as redundant exit points. I could use, it could be used for ECMP, but typically it's used for redundancy. And the node here, the node that's sending that traffic with that SID, it doesn't really need to know about those nodes at all. There's no state. It's not keeping track of those nodes. And I have redundancy at any point along the network. It's simply just IGP-based, and now it routes traffic across those nodes. And I can reference that Anycast SID in a static SID list as well. And that's typically the way it would be addressed. That way I can address that redundant pair of nodes with a single SID. Like I said, it doesn't have to be one node. It could be 100 nodes with the same SID, and it would load balance traffic across those. They don't necessarily even have to be in the same location either. They could be separated across the network, as long as they're in the same domain. So here's kind of an example of like how we do this, inter-domain with SR. And it really is using a path that's computed left to right that takes into account these SIDs. I do need to know what the boundary nodes are in order to create that inter-domain path. But you can see, like, here's my label stack there. Like I said, in SR, all the intent of the path is expressed on the first node. Like I said, with binding SIDs, you can, kind of expand those midpoint. But, at the beginning of the day, though, all that path intent is right here. And I'm basically doing, different label swapping and popping end to end at these boundaries. But I'm using this Anycast SID from this node to get to this domain, and this Anycast SID to get to that domain. So I'm simply just referencing that Anycast SID end to end in that static SID list. We look at TLFA, like this is TLFA is, potentially with TLFA I may use 2 labels. So when we talk about maximum SID depth and things like that, we typically include TLFA. TLFA will usually just use 1 SID for a fast route path, but potentially it can use 2. So that's why we usually show it in a data plane diagram like this. But how do we compute that end-to-end path? And I kind of get the cart before the horse, but I have this element called SRPC up here, and I'll get to that a little bit later. But at the end of the day, I'm just creating a path that takes into account these inter-domain boundaries to get my end-to-end path across the network. And again, that path can be statically configured. It can be dynamically configured as well. This is kind of what we have as a comparison between BGPLU, and this is why we would use SRTE and SR as an option over BGPLU. SRT, these are kind of our 2 types, but I get TLFA. Like even with inter-domain paths, with using that SID list, I still get TLFA across those domain boundaries. It's pretty hard to do that with BGPLU. You have to use BGP PIC. It sometimes becomes very complicated how you protect those 2 different domains. Again, I can use Anycast SIDs and TLFA as a redundant boundary. I can't really do that at BGPLU. The reconvergence time is usually pretty large with BGP, and BGPLU is no different. I could use BGP PIC, but then again, it gets kind of difficult to manage that. This notion of a PCE, I'll talk about that a bit more. The PC is sometimes kind of key to doing this inter-domain path. So like I said, I'll talk about that a bit in the future. Like I said, TE with BGPLU has always been a constraint. I could do TE per domain, where I might have RSVPTE, but I don't really have an inter-domain path that I can apply SLAs to or constraints to. So I've shown kind of how we can eliminate BGPLU, because I can define those boundaries. I can define how I address those boundaries end to end, along with these kind of different topologies. Kind of on the, one of the first slides, I showed kind of the 2 faces of SR, and one was this notion of simplification. That's a lot of where we've eliminated different protocols in the network and boiled it down to just IGP, the IGP with SR. But the other part of it was SDN and programmability. Like, what can I do with it that I can't do with existing protocols from that point of view? And that's kind of where we focused kind of the second aspect of the architecture of SR. And I talked a little bit about SRPC, and in that one diagram, I showed SRPC as a component of an interdomain path. But SRPC is an element that runs in XR. So how many people are familiar with PSEP or PCEs in general? A few people. So PCE is a path computation element. It's as simple as that. It computes an end-to-end path, from a head-end node to a tail-end node. And typically it does that for what's called a PCC. So a PCC is the client that's requesting the path end-to-end across the network. And we have a SRPC as a function that runs in XR. You could turn it on any XR node today by simply typing PCE, and it's turned on. And it can act as a path computation element for any other node across the network. Typically, we would say deploy these as, I'll say, virtual routers with something like XRV9K, because these can be completely out of path in the network. They don't need to be in the network path. But there's different ways that we get information into the PCE. It can be in an IGP adjacency to the network. Typically, we recommend using BGPLS. And I think I've got a slide maybe next that covers BGPLS. But this SRPC that we created, it does a path computation, but it's also API driven. So it supports northbound APIs, so I can drive a new SR policy into the network by talking to the API of SRPCE. So those are all open APIs that you could use to create new policies and tunnels across the network. And the big thing that we, from the very beginning, we meant for SRPC to support both single domain and multi-domain topologies. So we talk about inter-domain path calculation. The SRPC has the knowledge of every domain, and that's how it knows how to calculate a path end-to-end across the network when it needs to. So we don't deploy particularly an SRPC in every domain, and they talk to each other. We can have one or two SRPCs that each domain speaks to, and typically using something like BGPLS to feed it information, and then it can do inter-domain path calculation. And computing those, so it supports all of the, every node, like I said, has kind of SRPC integrated. So you don't need the SRPC to compute those paths, but the SRPC can actually take in, more information and utilize that information for, even kind of further constraints that can be used in inter-domain paths. Like I said, it's an SR process. You simply turn it on you type PCE, and it's turned on. And that's kind of all you need to make it work. Like I said, it collects the topology information, and that's key to how it does path computation, is it collects the topology for not only intradomain as well as interdomain use cases. And we talk about compute, shortest disjoint, low latency, SRLG-based paths, but we're always expanding that with new use cases. Latency is one that we're kind of expanding on even more by being able to do kind of real-time path measurement and being able to feed that path data back into the PCE so it can do basically real-time latency path calculation. So you're not just using kind of a static metric, you're using the actual real latency across links to do that. It's a Yang-based northbound interface. The API is actually very easy to consume, and that allows me to, go ahead. Bandwidth optimization. So bandwidth, we typically don't utilize this PCE to do it. We usually kind of talk to another application to do bandwidth function. With bandwidth, there's a lot of data to keep track of across the whole network. If you need to, if you have a very large network, and that data is typically not advertised in the IGP information. So today we use WAE, so WAN Automation Engine, could be used to collect bandwidth, information. If you go to Wordle Solutions, there's a new solution we have called Crosswork Optimization Engine. And that will be kind of the real-time element that does bandwidth optimization on an SR-based network. And so far, we basically have two specific use cases that we cover, which is bandwidth on demand, and then one that we call tactical TE in order to reroute traffic to around congested areas. And I'll talk about tactical TE. Our notion of a tactical TE is unlike RCP TE, where you're keeping the bandwidth state on the network for every path. So for RCP TE to really be useful, all my traffic has to be in a TE tunnel. And that state's carried everywhere on the network. With what we're doing with Tactical T, obviously we're moving that off the network onto a compute host. And then we're only moving traffic that needs to be moved. So we don't have a static tunnel for each piece of traffic. We'll look at, like, say, one high bandwidth flow and move just that flow in order to alleviate congestion. Right. Well, no, so it's interesting you bring that up because prior to, I think, XR 6.2, we did, an SR policy was a tunnel interface, just like RSPT. After 6.2, it wasn't flexible because when we talk about adding candidate paths and things like that, it just wasn't a flexible concept anymore, but we've added stats for all of those things. So you can actually not only get aggregate stats per policy, you can get the stats per candidate path. And I do a lot of peering stuff. There's a peering demo in the World of Solutions, and I'm actually using model-driven telemetry with those statistics to drive some behavior. Yeah. So I'm not going to say that initially when we went to the new architecture, there were gaps and things like stats, but as of now, we've solved all those issues. Yep. And it's all Yang model-based, and all of that. So, like I said, I kind of talked a little bit about BGPLS, but BGPLS is BGP link state. It's not something new with SR. It was really a way that I could advertise my topology using BGP, which is a very scalable protocol, to an external host. And it was really meant for PCEs to consume topology data, as opposed to having an IGP adjacency between my PCE and the rest of the network. Now it's simply a BGP session. It could be anywhere, not even on the network, to compute that. So like I said, it's a specific AFI-SAFI, but it's been modified to support SR as well, though. So when you talk about SIDs being advertised, that information being advertised, it's all advertised via BGPLS. It's also been enhanced to support what we call like performance data. I talked about being able to do per link latency measurements. That data is also exported into BGPLS, or I'll say it's exported into ISIS and OSPF, and then exported into BGPLS. So it's kind of become the Swiss Army knife for advertising information to compute hosts, whether it's a PCE or some other type of device. The other nice thing is it scales. Since it's BGP, it scales using route reflectors. I don't have to have a session from every router back to my PCE. I could simply have what we call like a transport route reflector and have sessions from that, from each domain on my network to the route reflector, and then it has the session to the PCE. And you basically get real-time updates over this as well. So when a change happens in the IGP, it's immediately reflected and advertised via BGPLS. And here's sort of the PSEP slide. And like I said, I won't go through all of this because it's a lot of data. But really, the two important things to note is the PCE, that's what does the path computation, and the client is what requests that path computation when it has some sort of path that it doesn't either know how to compute, or it may be better for the PCE to compute that since it has more information. And today, everything is stateful. Within the last, originally PCE, it's been around for 14 years, I think now. But originally, it was very stateless. My PCC would make a request, I'd return a path, but the PCE wouldn't keep track of that path. It wouldn't keep track of what it had signaled, and vice versa in the state between the two. But now we have something called stateful PSEP, and it's both for RSPT and SR. So I always have this state between the two, and the PCE always knows the path. It knows which paths it's computed. It knows the path that it's taking. And that way, if some sort of change happens that it knows about, it can change the path as it needs to. And that's where we see this notion of state synchronization between the two. Here's my one NSO slide. I think folks are mostly, NSO, when we talk about gluing the entire network together, NSO becomes more important. It's not really a transport level element. It's not doing BGP, service signaling. But when I want to kind of provision a service end-to-end, when I want to provision all these kind of different attributes, NSO becomes very important for doing that. So we definitely usually include that as part of a holistic solution that we're trying to solve because it's very good at what it does in things like service management. here's kind of an example of kind of what happens, in the case where I do want to compute, I call like a end-to-end SRTE path. And this path doesn't have to be interdomain. The PCE becomes more important in the interdomain use case, but you could use it to compute intradomain paths as well. There's nothing that says that. But typically, like our workflow, like I said, NSO is very kind of important in provisioning the service layer attributes. That's where you talk about, your VRF, your RT, your RD values, things like that across the network. But when I do that to this A node, if this A node, doesn't have a path to say a destination, I can have it consult the SRPCE to say, hey, I need a path to that far end node for that service. And the SRPC is what instantiates that, it's what returns that path to the node. Because like I said, the node may not know how to get to that far end destination. It may be an interdomain path. I don't have BGPLU anymore to give it a path. So the SRPC is really what's replacing BGPLU and stitching together those interdomain paths. And at this point, this is a two-way session. It's basically a peering session between the two. And like I said, they keep state between the two at all times. And here's like kind of I showed this diagram before, but now when you see the SRPC, you see the communication that happens kind of end to end as that SRT path is instantiated. The example I just showed, I do my service provisioning here, and it requests a path from this SRPCE. The SRPC knows how to get to this node because it's using BGPLS, between these nodes into these route reflectors. So all of the topology information, you can think of this as this access core and access. They're not part of the same ISS domain. You can think of them as three completely separate level 2 domains. They have no connection to each other. They don't redistribute any routes or any topology information. All of that information is stored in the PCE. So the PCE knows how to create that end-to-end path across these three completely disjoint domains. And we use that as a scaling mechanism because now I don't have to distribute information between domains. And I can extend this. This shows 3 domains. It could be more domains. I could have access domains that, hang off of this access domain, especially in really large networks. We talk about like mobile backhaul. You're potentially thousands of nodes. So we have to have a scalable solution that supports those large networks. Like we have BGPLU networks today that are 300,000 nodes. So we have to find ways to support that with this simplified mechanism as well. This kind of gets to an advanced use case, and I'll say a Cisco feature that we use to simplify how all this works. We have this feature, we call it ODN. You'll hear most people talk to it as ODN, but it's really called On-Demand Next Hop, and I'll get into a bit on how that works today. So we have this notion of like an on-demand SR policy. An SR policy, again, is an end-to-end traffic engineered path between a head-end and an endpoint. I said again, an SR policy is defined as a color and an endpoint. And really, when you think of color and endpoint, the endpoint typically with VPN services, that's your next hop. That's the BGP next hop for a VPN route. And that's really, in the context of I'll say a legacy MPLS network, that's how I build my end-to-end MPLS path across the network. So in this case, my endpoint for that policy is typically always the BGP next hop. And the color is how I define, really how do I steer traffic into the policy. The color is also a way that I do that. And I could do that through using what we call a BGP color community. And the color community isn't new. It actually was defined in the RFC, I think, 5500 days. We're reusing it to uniquely identify the constraints or SLA for that route. And we use that on the head-end node. We match this BGP color community and the BGP next hop. And what that allows us to do is automatically instantiate an SR policy, so we don't have to build one ahead of time. So when we receive that route from the far-end host, that VPN route with that specific next hop, we know to build an SR policy to that end node. And the color actually identifies the constraint. So on that head-end node, I match the color, and the color matches a policy that says what constraints apply to that specific policy. So I can have a color that's associated with latency. I can have a color that's associated with, like I said, high bandwidth or just IGP metric. The key, though, is that it's not only automatically instantiating the policy, but it's steering traffic into the policy based off of the prefixes that match that color. Like I said, it's simply an extended community, just like an RD or an RT value. So when I advertise the routes for a specific VRF on an egress node, I tag them with that color, and the traffic automatically gets steered into a policy that matches those constraints. Like I said, everything with SR, we try to make it fairly simple. So typically what I do on every node that's using, say, ODN or color-based steering for traffic, I'll define the same color on every node that applies to a certain metric type. In this case, we're using a metric, this metric in order to define our constraints. In one case, I have IGP. In one case, I have TE as a metric. And those two different metric types, IGP is simply the IGP metric that it's using. The TE metric lets me actually statically assign a metric outside of the IGP metric to be used for kind of other use cases. Originally, we used the TE metrics to support low latency use cases, but now we do have sort of real-time measurement. Because previously, you could statically assign certain metrics on certain links that were different than the IGP metrics. So it gave me two different mechanisms to kind of steer traffic using IGP attributes. But again, once I match these, I basically create an SR policy specific to those constraints. Yeah, whether it's a high bandwidth IGP metric or 20 for a low latency. Here's kind of another example. I showed the example with NSO, but this is sort of the example of how ODN works end to end. Like I said, typically I have a BGP route, this 1.1.1.21/32 on this 21. It says VRF blue for that. And in these use cases, I'm basically showing a VRF or a layer 3 VPN use case, but it doesn't have to be in a VPN. We support the same mechanisms for like the global table. For instance, in a lot of the peering things we're doing, that traffic's in the global table, but all these same things apply to the global table. You're still just using extended communities to sort and steer traffic into certain policies. So CE21, basically, and this is kind of starting at the CE layer. So at my first node, PE22, I check a policy, and I find that I have to, that's a low latency prefix. And I can simply match all prefixes. I can match certain prefixes. But what I'm doing is I'm tagging them with this community. And like I said, it's an extended community, just like an RT value. This specific 100.777 corresponds to a color that means low latency across the network. Like I said, it's sent, in this case, these are route reflectors. I'm using like a BGP service route reflector. But eventually it's sent to, PE3, which is my ingress node that's also in my VRF blue. So what happens, when it receives it, it matches that color. There's a policy that tells it that, hey, I need to consult the PCE to get a path to that next hop. I don't know how to get to that next hop. That next hop doesn't have to exist as a route on the ingress node. It will go to the PCE. Since it doesn't already have a path to that node, it will use the PCE to get there. And it'll use my, like I said, originally we used the TE metric to, kind of represent a low latency path. So in this case, it's actually telling the PCE what its constraints are. And that's one of the other keys is we communicate what the constraints it actually needs to the PCE, so the PCE can compute those end to end. So it returns basically this SID list across the network. This just happens to be the path that is my low latency path across the network. So it'll return this SID list of the segment 5, segment 14, and then segment 22 to get end-to-end to this PE node. And like I said, I mentioned earlier, it creates a binding SID for that path that kind of abstracts the underlying candidate path from what the, I'll say the BGP process needs to access in order to steer traffic into that policy. So BGP actually uses this 30,022 SID for that VPN4 route on this PE node to steer traffic into that. So it's a kind of an elegant way for it to compute on demand the paths that it needs for specific services and specific SLAs. One thing I'll say about the SRPC is when we compute paths both on the node and the SRPC, it will optimize the path that it needs. So Just because you need like an end-to-end path that may go through all from 5 to 14 to 22. In this case, I'm showing like a SID list of 5 to 14 to 22 because I want the path to explicitly go through this node 5, potentially. But let's say I just needed the path to go through 14 and not those other ones. It'll compute the optimized path. It'll compress the label stack to what it needs to in order to support that. And if my path had been from 3 to 14 to 22, there's a potential, like if these were ECMP paths, it would use ECMP across the network as well. I think one thing important thing to mention with SR is you don't lose ECMP capability end-to-end across the network at all, unless you want to. I can create an explicit path like this that says, hey, each node of the network needs to use that path, or the path will go through each node, but I don't have to do that. I talked a bit about what we call like SR-MPLS performance monitoring. And like I said, it's as simple as per link delay measurement. And it's used as a metric in my SR policies, as well as something we call flex algo. And this is not a pure Cisco invention. This has actually been around for a number of years. But it's somewhat difficult to do in the data plane. It's somewhat difficult to do on the node, but it's something we've implemented today. It's advertised in ISIS and OSPF, and that's what makes it available to the PCE through the BGPLS information. And you can read about it in this IETF draft. I talked a little bit about flexible algorithms. This talks a little bit about some of the, I'll say, more advanced traffic steering capabilities that we have with SR now that have come up kind of recently. The idea with flexible algorithms is that you have that notion of a node SID with a prefix SID to a loopback address. Now what I could do is I can actually create what we call a different algorithm for different colors and different algorithms, I'll say, for different prefix SIDs. And I'll get into an example. It's a bit easier. So here's sort of like, about the only header stuff I'll show is, so now associated with a specific prefix SID, I have an algorithm that belongs to. And that's, that algorithm kind of 0 means, just best effort. But I can assign, an algorithm value to that that really can be used to express a path end-to-end across the network that matches a constraint without having to actually use an explicit SID list. So it's better with an example. So one kind of the most basic use case that we usually talk about is this idea of like a dual plane network or a multi-plane network. In this case, I've got all these nodes. I've got 2 different paths, obviously, on the upper and lower. They're all assigned to this, the SID on this 9 node. So like I said, I've got one loopback address that I can apply. I can actually assign multiple SIDs to that, each one to a different algorithm. This 16,009 is algo 0. And what algo 0 really means, all these other nodes are assigned the same algo 0. So if I use 16,009 on the 0 node, it can really use any path to get to that end node. But then I also have 2 other SIDs assigned to that node. I've got a 809 and a 909, each on different algorithms. And 128, like I said, in this case, could be minimized IGP metric. One could be minimized delay. And what it means is on this 0 node, I just simply use this one SID, and I'll only take the path through the nodes that belong to that SID. Well, I said the original intent of kind of this draft and this mechanism was dual plane networks. But we have more advanced use cases for this today. Like one in particular was if I want my network to only take like MACsec encrypted paths across the network, I can assign a specific flex algo algorithm to all of my MACsec links. And if I have a certain traffic that I know has to be MACsec encrypted, it will only take MACsec encrypted links. And I could do that with just one SID. I would have to create an explicit path to do that. And I won't go through all the use cases for flex algo, but there's a lot of similar use cases to do simplified traffic steering by just addressing that one SID. Sort of the animated version of what I just talked about. And like I said, kind of another example is, like say I want low-cost paths across end-to-end across the network. I may simply just use algorithm 0, which is best effort, across that. But again, I can steer traffic into those flex algo paths using ODN. So something we have coming very shortly is ODN with flex algo. So I'll have the ability to reference a flex algo, and usually that just comes into like PCE extension support and things like that. So these are things that we do flex algo today. We're mixing that with ODN to be able to steer traffic into a specific flex algo path. Like I said, the next, I could use this to also steer kind of low latency path across a completely different path if I need to, just by referencing this one, the prefix SIDs that are associated with that algorithm. I only have a couple slides with SRv6. So SRv6 is just another data plane. Like I said, SR is more of an architecture. It is flexible as far as things like data plane. So where we're looking probably a bit in the future is SRv6 with a v6 data plane. In SRv6, instead of using an MPLS label, I'm using a v6 address. V6 address is my SID. In this case, I use something called a segment routing header, and I add a segment routing header for each kind of v6 SID in the path that's there. And it's just another segment routing extension header. And since it's based on just IPv6 routing, if I don't need to explicitly address a node, it runs over just regular v6. The destination for each SID is just a v6 address. So unless I'm actually, making a node a midpoint, it's transparent to all other v6 nodes, which makes it pretty elegant to run over an existing v6 network. Like I said, everything is a 128-bit address. We also have this notion with SRv6 that we're looking at. Go back, skip through the animation a bit. We have this notion of a locator and a function. And there's a good draft, and I don't have on here, around network programming that we're doing with SRv6. And the idea is I've got a lot of bits to play with. I could address usually an entire router with like a /48 or a /64. I can get I can use that as my, I'll say, locator function, or locator address to get to that function. And I'm sort of what I call overloading the v6 address, and I'm embedding my service layer properties within the v6 address. So now I maybe don't need signaling for a VC label for a pseudo wire. I don't need additional layer 3 VPN signaling. I can embed some of that signaling information within the v6 address itself. And it's basically eliminating another layer of complexity of, I'll say, data plane headers on the network, just by embedding that information in v6. And one thing that's somewhat elegant in that is if I'm using I could basically, if I know the destination and I'm using this, say, locator is like 2001-4 are the bits that I'm using to get to this end node. And my function is E100, and E100, it decodes to this function, which means IPv6 layer 3 VPN, and this is the VRF. So I'm embedding that information in the v6 address. And to get to this end node, I don't actually even need an SRH. I just need a v6 address. And the idea is that with the I don't need interdomain path computation. I'm just simply doing like address aggregation. So if I'm using, say, a /40 for each one of these domains, for this domain, I'm just using IP advertisement and redistribution to get end to end. So unless I actually need static paths or static hops across the network, I can just use a v6 address end to end. Like I said, it greatly simplifies everything. And like I said, what we're working on today is support for both hardware and services for SRv6. So look at it as more of, I'll say, an end of 2020 type of thing. Today, SR MPLS, we support pretty much every service, every type, every advanced SR function, but we're working rapidly to get SRv6 support as well. Yeah, so there's an IETF draft called SRv6 network programming. Yeah, and it defines all of these functions. So there is this is a kind of convoluted example with this E100. If you use the actual standardized kind of bit masks for that, it may not be E100. But there's definitely a list of probably 10 or 12, I think at this point, functions and how those are addressed. And it's meant to, that the locator portion be flexible. I'll say that becomes a little problematic because hardware is typically doing forwarding on defined boundaries. If you have to look for boundaries within an IP address or an IPv6, that becomes a little more difficult for hardware. So it's best to have, like today, we'll typically use a /48 for a locator function, and the rest of it will be a 48 or a 64, typically. Like I said, interdomain, that's where we require, and if I'm doing like specific traffic steering from like 3 to 5 in this domain, that's where I still have to insert what we call a segment routing header, and it has the segment list. Like I said, I'll go through this pretty quick, but simply like when you have a segment list, all it's doing is copying at the node that's SRv6 capable that needs to send traffic to the next node, defined node. It simply copies the segment list into the v6 destination address. Like I said, it's all just regular IPv6 routing at this point. So when you have a specific segment list, it just copies that segment to the destination v6 address. And it keeps the locator function kind of intact end-to-end across the network. Or it can change based off, like we have examples of doing like NFV type services where you can basically use this function to specify a specific, say, like an NFV firewall type service specifically. Like there's a lot of use cases because of the amount of address space you have with SR. We have use cases where using specific SR addresses to, if folks are, things like video delivery using like Apple HLS, like each chunk is a different v6 address. So you can use a v6 address to address almost anything. Through these locator functions, you can support a pretty wide variety of network functions pretty easily. So we talk about, I've talked a lot about SR and how SR is used for transport for these kind of next generation networks, but what are we doing to build, I'll say, services on those networks? And that's where, BGP-based services and specifically Evpn come into play. And is anyone running Evpn? Lots of people, yeah. So Evpn is not new. Evpn is not a Cisco invention. Evpn has a lot of vendor support across the board. And it's really, Evpn is one of those things where like, you wonder like why we didn't think about this, like 10 years ago. Because we use layer 3 VPN, and it's analogous to layer 3 VPN, but we created these convoluted ways to do multi-point layer 2 services through VPLS and all those things. And you look back on it and you think that makes no sense, but we did it anyways. So really, it's the next generation of control plane for, like I said, Ethernet services. And really, the original intent, multi-point was kind of the first where it started, but it's definitely been extended to support things like Evpn VPWS, which is point-to-point, pseudo-wires, for lack of a better word, as well as this notion of like Evpn IRBs. And I won't get too much into that. My colleague Yuri Chalupka has a really good Evpn deep dive where he'll talk, about all this stuff in depth. But IRBs really allow us to do, active-active, I'll say layer 3 multi-homing with Evpn. You can think of it really as a replacement for something like VRRP and creating a redundant gateway in a better way than what we've done in the past. Like I said, we're still trying to be a leader in this. We're active in most of the Evpn drafts and a lot of the things that are being done with things like multicast in Evpn and try to push optimizations that way. Kind of quickly go through this. Kind of the important parts in Evpn to keep in mind is this idea of an Evpn instance. So that's kind of the overarching instance that defines a global Evpn. And that has things like RTs and RTs attached to it. And this notion of an Ethernet segment. A segment really is what identifies the connection to a layer 2 domain. It's as simple as it sounds, an Ethernet segment. And it's used to identify uniquely, like I said, that Ethernet segment that this CE is connected to. It's really used as to define whether a device is single-homed or multi-homed. Kind of the elegance of Evpn is that I can have a multi-home device with the same ESI, ESI2 connected to both of these. And the control plane determines what's the best way to forward traffic on that segment. Obviously, you can't forward say broadcast traffic across both active segments at the same time. But Evpn takes care of a lot of that complexity. I won't go through every route type. That's more for Yuri's presentation, where we talk about how we actually discover the endpoints. And like I said, for lack of a better word, we're doing MAC routing instead of IP routing in Evpn. And a lot of these attributes are used for, like I said, things like mobility, as well as multi-homing capabilities within it, like I said. So we're doing for MAC bridging. VPLS, we're just trying to emulate a big layer 2 switch and all the complexities that come with that. We've eliminated that and replaced it with what we really consider MAC routing. But it's not just applicable to data center networks. We saw a lot of Evpn, especially the VXLAN, used in data centers even today. In the access, we're using Evpn for all types of layer 2 services. But it really allows us to kind of simplify those kind of layer 2 overlay networks with a single control plane protocol. And obviously with segment routing, we kind of tie together the transport network as well. Like I said, here's just a couple of the issues we see with things like VPLS. Like I said, it's really kind of a big layer 2 switch. So you run into all the complications with that, with things like duplicate frames across core networks. When you do have load balancing that's happening, typically you can have devices in the core that they load balance not based off a MAC address. They're based off of some sort of layer 3 information. So when you have kind of dual home across the core, the PE nodes on this side, they could be getting based on the hashing on one of these nodes. And like I said, VPLS is like a layer 2 switch, so it does data plane learning. So it learns based off the data plane, and that could flip back and forth. There's a lot of common issues with VPLS, especially with multi-homing. Single home is pretty simple in VPLS, but multi-homing brings a lot of issues. One thing that we try to do, these are kind of all the services that we can cover with Evpn. E-line really is point-to-point service. ELAN is your multi-point VPLS type service. E-tree is obviously a point-to-multi-point, typically used for kind of distribution or security reasons. Other things like DCI, DC fabrics. One thing you'll hear us say at Cisco is we're not actually trying to replace layer 3 VPN with Evpn. If you read drafts, if you read a lot of information, you will see things around layer 3 in Evpn, even things like we call inter-subnet routing now, which is not really even like stretching in a single subnet, but it's really doing routing across Evpn. There's still a lot of good use cases for layer 3 VPN. For customers that are strictly like layer 3 based, oops, sorry. We're not trying to replace layer 3 VPN. We've had 10 plus years of investment in layer 3 VPN, and honestly, if you have customers that are doing CE routing that's either mostly BGP based, you can't really replace that with Evpn. There's a lot of people who might want to do that, but that's not our vision of how we see Evpn and layer 3 VPN evolving. So like I said, we're not trying to replace layer 3 VPN end to end. Like I said, these are just some of the advantages. And people that are familiar with Evpn, obviously, and MVPLS, I don't think I need to espouse what's better about Evpn. There's a lot of things. I'm not using BGP learning and not data plane learning. I'm not using, say, full meshes of pseudo-wires. There's a lot of benefits to using Evpn auto discovery. It's supporting both v4 and v6. And one important thing we try to say is multi-vendor. It's hard to find any vendor today that's not supporting Evpn just because it makes sense to do that. And this is like a good diagram of how really when we think about layer 3 VPN and Evpn, they're really identical in the way they operate kind of at a high level. Apart from using an IP packet in layer 3 VPN versus a layer 2 frame in Evpn. Like I said, it would have been nice if we had thought of this many years ago because it's a much better way to do layer 2 services. Exactly, and today this is kind of an interesting diagram. I didn't put this one together, but we talk about Evpn for SP networks and data centers, and they're really the same concepts. It's using the same control plane. They're very much the same, and we support the same services, whether it's an SP access network like cell backhaul, or a data center, where we're doing Evpn on a top of rack device. It's really the same concepts when it comes to things like multi-homing, and it's used in both use cases. In this case, it's as simple as, active-active is a good thing for EVPN that I get over in a simplified way over something like using MC lag. You could think of this, I don't have a deep dive slide on this, but it's really a good MC lag replacement. MC lag carries a lot of state. MC lag is typically always proprietary with each vendor. EVPN is a standard way to do active-active multi-homing or active standby multi-homing in a, like I said, a vendor neutral way. Like I said, it typically, like I said, it's not an EVPN deep dive, but I simply use the same Ethernet segment identifier to identify which is an active-active host to note so that these nodes know that I'm connected to the same Ethernet segment. So they do things like forwarding elections so that I'm not sending broadcast traffic down both links and particularly flooding the network. We talk about these active modes. You can find these in the RFCs and the drafts for EVPN. Everyone uses the same naming conventions for these. All active is really what we're talking about is per flow. I'm hashing traffic in an active way to say both PEs. And that's kind of a simple way. Single active we consider per VLAN. And really that's the case where I have two bridge domains. I may have the same service with two different VLANs connected to the same set of PEs. But these are really like using different Ethernet segment identifiers. It's really, the concept is really they're kind of two separate services within one EVPN instance. The other is what we call port active, and that's something that we're trying to kind of lead in some ways is the ability to do active standby. And this comes a lot with customers that they want the redundancy, but especially with things like QoS, it's very difficult to do QoS across two different boxes. Nobody really supports that. So for a customer that has an SLA, like they might have a 5 meg service, you don't want them to get 10 megs out of it. So typically you're using an active standby service to limit them in bandwidth and things like that. And this way you can have a port that's in standby all the time, and that's all signaled through EVPN. So, like I said, this idea of a designated forwarder, and again, this is all signaled through EVPN, the EVPN control plane when I'm dual connected to the same Ethernet segment. I have to elect a designated forwarder, otherwise I'm going to send duplicate traffic everywhere. I want to know which MAC addresses are connected to which forwarding element to that same ESI. And through that advertisements, I know exactly where to send traffic end to end. Also things like split horizon. VPLS solves this problem kind of as a data plane mechanism. In EVPN, we solve split horizon and sort of unicast traffic by using special labels so that the labels indicate that I should not send that traffic back out to the core network. So and that's signaled across the entire EVPN. So it knows use this label for this specific type of traffic. It means don't send it back out the same interface or back to the core links that I received it from. Also this notion of, we can easily signal like a mass withdrawal when we have failures. It's as simple as setting 1 bit to 0 and advertising that out everywhere. It'll withdraw all the MACs so they could reconverge to a new device much faster. And again, Yuri will go through like how all that mechanism works in his deep dive, but it's a very simplified mechanism that's been there since kind of day one for EVPN. Similar with, I showed kind of broadcast, unknown unicast and multicast traffic. It is really optimized by using this bum label to make sure looping doesn't occur. I won't talk too much about multicast today, but there are multicast efficiency mechanisms within EVPN to limit, say, who gets multicast traffic. Today, most traffic with our devices, we carry multicast through ingress replication, but we do optimize that by only sending traffic to nodes that have, say, interested receivers. If you want to know more about EVPN multicast, just catch up with me after we're done. We also have this notion of like aliasing, and that's a case where I do have reachability to the same domains via sort of 2 different hosts, but I'm only learning that through one host. And that's a mechanism where I can advertise that same MAC via multiple nodes that I know are connected to that end host to better load balance traffic to that host. This gets into potentially a more complicated topic, but this notion of, we call it Anycast IRB or Anycast, Anycast gateway. And it's a way that I create, a distributed gateway for all of these, I'll say layer 2 connected hosts below here. And it means that I've got the same, gateway that's identically configured on all these leaf devices that can act as a redundant gateway for all these hosts. And when they move, these are all using the same, say, destination MAC. So if I have a VM that's mobile underneath here, it still continues to use the same gateway MAC and the same gateway address end to end. And these Anycast gateway information is advertised, through the Evpn control plane. So it knows when they appear, when they go around. And like I said, unlike something like VRP, I guess VRP you could have more than 2, but in this case, I could have 128 Anycast gateways if I wanted to. It's a very scalable solution for doing a distributed kind of layer 3 gateway. In this case, where I have a network fabric, and with Evpn, we can support kind of basic layer 3 routing as well as layer 2 on the same service type. So that way, I'm not running, particularly if I need layer 2 and layer 3, I'm not running both layer 3 VPN and Evpn. I could support 2 on the same service. Something that came a little bit later, but it's very important, is this notion of VPWS. A VPWS is nothing but point-to-point pseudowires that are Evpn signaled. It's a very simple concept, but I could use like per EVI discovery to discover those endpoints. It's all signaled through BGP. So if you're familiar with like BGP AD and auto discovery for say point-to-point Ethernet services, a very similar concept, but using Evpn to do all that signaling. And it still supports all the same Evpn multi-homing and signaling as I did with the other use cases. Another thing that's kind of important is the ability to integrate, I'll say, a layer 2 Evpn domain to a layer 3 VPN domain itself. And we support, there's a certain route type in Evpn, route type 5, that has the ability to advertise an IP prefix through an Evpn. And we have the ability at a border router to take that route type 5 and advertise that into a layer 3 VPN. So it really allows me to interconnect a layer 3 VPN to a layer 2 VPN with layer 3 routing. There's a lot of interesting use cases with that. Like I said, Yuri's talk will go into that in a lot more detail. And I could also do route summarization here. So if I have, I'll say, a lot of like CE2 devices here that I'm advertising IP prefixes for, I could do summarization on what we call the DCI or border leaf node. And it basically simplifies the routes. Like I said, there's cases where this CO or this data center, there may be thousands of those devices where we want to do address aggregation on this node. And that's kind of an example of how we use these RT5, which is the prefix route type within Evpn, to convert that prefix into a layer 3 VPN VPNv4 route. So at that inner working node. And I'll say today we typically support those kind of DCI functions in XR on the ASR 9K devices is what we typically would use for a DCI border leaf node. We could also connect, from a legacy point of view, any type of layer 2 domain, we can integrate that into Evpn. It's simply that interface or that VLAN is just an ESI. It's an Ethernet segment to Evpn. No matter what that layer 2 access technology is, we can integrate that in. I'll say it's not so represented here, but we support this notion also of like a virtual Ethernet segment. So if I do have an existing VPLS network or an existing, I'll say point-to-point pseudowire, I can connect that to a virtual Ethernet segment. So I can dual connect an existing VPLS to an Evpn domain by using a virtual Ethernet segment on 2 different Evpn nodes with the same ESI. And it's just one way I can help integrate those kind of 2 networks together in a more seamless way. We also, support a service or a mechanism we call seamless VPLS to Evpn migration. And that's a mechanism on the node where we configure a single bridge domain with both VPLS and Evpn. And we prefer the Evpn signaling over the VPLS. So what I can do is I can migrate hosts or nodes over time to Evpn And that bridge domain will figure out which mechanism to use to get to those MAC addresses. It'll learn them via both data plane learning and EVPN, but it'll basically prefer the EVPN route so that I can then turn off VPLS. And it gives me a seamless way to migrate to EVPN. We call the feature seamless migration, but you could use it to connect to a VPLS, forever if you needed to. It's really an integration mechanism. I won't talk about this too much, but I talked about the notion of an Anycast SID. We can do the same thing with like a simple layer 2 pseudowire. Go ahead.
On that previous slide, were you the A1 to A1 into A2 there? Is that all just running straight layer 2 there? Is that a metro ring?
Yeah. So that could be a layer 2 ring running any of those protocols.
So where's the actual ring then between the PEs?
It's transparent. So yeah, so between these PE and the EVPN domain, like that signaling traffic is kind of transparent across that EVPN domain.
So it's actually able to transport
Yeah.
STB rep or
Right.
to
Yeah,
the
transparently.
EVPN?
Correct, yeah. So you don't lose that kind of signaling mechanism that it's using end-to-end. I will say that you don't get the G8032 and rep like 50 millisecond protection. It won't happen if you see a failure in this domain, because obviously, that's, dependent on signaling that happens within EVPN. That's the only caveat to kind of transparently connecting these across that domain, I'll say, is that, yeah, failures that happen in this domain are typically, obviously it depends on the failure type. But if you had, say, a AVR node failure here, typically that would be a longer, actually not the node failure, but there could be failures in here that take longer than 50 milliseconds. That's why we kind of look at this as, it's a migration technique until you can, say, migrate hosts, to kind of a layer 3 IP and PLS access. Now, we do have the ability to, run rep on these nodes as well and interconnect those. There's a couple different ways you can do it, but it gets a little messy. Like I said, this is a very simple method, and this actually, it doesn't really use EVPN in this part of the network. EVPN is, kind of starts on what we call these core PE nodes, but in the access, I'm using a notion of an Anycast pseudowire, and this is a statically configured pseudowire, so I'm configuring the VC label and the endpoint for this Anycast pseudowire, and I just point it to these Anycast SIDs. I just point it to one address, and it gives me instant redundancy without any signaling involved. And a lot of customers, they use this in cases where they want to keep their access network just using one service type, like this Anycast pseudowire, and they host the more advanced service, like layer 3 VPN or EVPN, is on another node. We typically call this a hierarchical service, meaning that we're using one type of service in the access, and the core is a different type of service. And like I said, and really it's up to different customers. They could start the EVPN service here if they wanted to and use end-to-end signaling. But in some cases where they have many types of servers like layer 3 or EVPN, different types of EVPN here, and they want to keep the access very simple, they'll use something like just a single Anycast pseudowire to do that. Another use case is folks that are familiar with things like pseudowire headend. Pseudowire headend is a way that we do kind of scalable layer 3 on these sort of PE nodes, and it's the same notion of a hierarchical service. We're using just EVPN VPWS across this access domain, and this may be like say a more complex service. In this case, it's an ELAN type service, but it could be layer 3 VPN as well. But it's a way that we create kind of hierarchy in our services to potentially scale higher. So when we look at EVPN end-to-end, as far as like service layering and what we can support in EVPN, it's obviously very, very flexible today. I didn't talk about FXC. FXC is flexible cross-connect. If you have questions about that, just let me know. But really, I can support all these basic services within that single EVPN control plane. So we kind of look at like end-to-end how we build this, in modern networks. How do we tie together EVPN and SR and those layers together? And This is sort of what we call our converged SDN transport design, and it is sort of the modern way we address all those layers of the network. Like I said, it really starts with NSO as a service provisioning piece across all the domains. And the SRPC here is, like I said, in this use case, this is an inter-domain use case because these are different domains in the network. So I'm using SRPC. It is the mechanism for doing inter-domain path computation. I'm using PSEP, I'm using BGPLS to give the information to the PCE and communicate to these access network hosts. And the end-to-end within each domain, I'm using the IGP with SR extensions, and that's it. That's the only thing I'm using for intra-domain and inter-domain MPLS transport across the network. The idea is that all of my services are now using this single BGP control plane. There's no more LDP signaling across the network. There's no pseudo-wires that you'd find in, say, BGP-AD or LDP-based VPLS. It's just a single service domain with L3 VPN and all layer 2 VPN using Evpn. And this is here today. It's not a future thing that we're looking at. This is all stuff that can be implemented today.
You guys working with other vendors for interoperability from your PCE?
We do. So if you do a search for like Cisco and the EANTC, and it always coincides with MPLS World Congress, which happened about a month and a half ago, there's a huge interop event there. And we not only test the data plane type stuff and the normal signaling, but they do a lot of specific PCE tests. And I'll say today, multi-vendor, especially in the SR realm with PSEP, has its challenges. And usually it comes to how new things are and how fast they're being developed. There's definitely drafts that have consensus from every vendor on most of these things. But kind of speed to market, not everything, some things are pre-standard. But you can find a good report that was actually just published on that from EANTC, and it's generally between Cisco, it's Nokia, Juniper, Huawei, as well as some other vendors that are maybe PCE only. This kind of shows the use case where we really scale this much higher by adding these route reflectors. So I've got route reflectors. All my services are BGP based, so I'm disseminating routes simply using BGP to these service route reflectors, and then I'm introducing this notion of a transport route reflector to distribute BGPLS information. To do the end-to-end path, each one of these SRPCEs has to have a full view of the entire network. Today, and maybe something we're maybe working on in the future, it'd be good to get some feedback, is we don't have a notion today of a hierarchical PCE, but it's definitely something we're looking at in the future. So today, every PCE needs to have a full view of the whole network. But in the future, to even a higher scale, we may look at hierarchy in PCEs as well. And addressing domain boundaries with these Anycast SIDs. Like I said, it gives you an easy way to have a redundant boundary between nodes, and also support things like TLFA across boundaries by using Anycast SIDs on these two nodes. Here's, like I said, here's kind of the data plane end-to-end that I need to address, say, this A2 node from A1. So I'm basically using S1, which is my Anycast SID 1, Anycast SID 2, to get to A2. And this kind of gets to what I talked about with some of the optimized forwarding that, say, SRPCE can do. And that this access domain may be full of other nodes that are in the path, but it doesn't really care about those nodes to get to A2. So it'll only build a SID list on here with the hops that it needs to get to the end. It's not going to have extraneous hops in there unless there's some sort of constraint that it's trying to solve where it needs those hops. In TLFA, like I said, the two labels is if they're needed. Under steady state, those aren't needed. Typically, we could protect with one label. But like I said, there are use cases, especially with ring networks, where we need two labels to provide the TLFA path. So really, when we look at this design, the main components are the things that we want to do is each domain is running SR. The area border routers, we're using Anycast SIDs for HA. And the SRPC becomes kind of a critical element, for both the intra-domain if I have constraints, but especially to compute inter-domain paths in a scalable way. And like I said, I mentioned using on-demand SRTE, and all the Evpn services that I talked about we can use ODN with those in order to trigger the paths and steer traffic into the paths dynamically. And some of the use cases we're seeing today, obviously things like 5G. 5G is, not here in some form for some people, but lots of people are looking to build 5G networks today. We're looking to scale. Obviously, there's lots of endpoints with 5G, so you need a scalable way to build networks to support all those endpoints. So this type of design and the converged design is what we're doing end-to-end. And Cisco's designed to cover 5G is SR and BGP-based services end-to-end. So there's no L2 on the network. It's all layer 3 based end-to-end. From the even edge nodes, where we're doing things like mid-haul and especially backhaul is all today IP MPLS based, but moving to things like SRv6. And really something that we've done a lot with SR these days is around converged access. There's a lot of networks today at SPs that use fairly siloed networks between service types. And since and this isn't a product pitch at all, but we can, on these leaf nodes today, which might be an NCS node like a 540, or even in some cases like an ASR 920, we can support lots of different services on those edge nodes to support kind of any type of access service. So we have folks today building highly converged networks to support any of these service types on really any leaf device. Like I said, it's a way to build kind of more scalable access networks and have one device type and one network that's handling all these different traffic types. Cable is another area where we're doing something very similar. Like I said, this diagram is kind of translate to this, and it's where cable networks are sort of transforming with things like RFI and converged interconnect networks, but they want to use those networks to carry not just cable traffic, but it might be PON traffic, it might be mobile backhaul services. We have customers today that are using basically segment routing and EVPN to build network fabrics to support all of these services. And here's sort of the conclusion slide. I guess I'm only 2 minutes late. Like I said, it's really a simplification journey. That's really the point of kind of why we're doing all of this and all of this work is to simplify how you deploy networks and deploy services. While trying not to forget about how you migrate to that. Like I said, we've had ideas like SR and LDP interworking since the very beginning. And this idea of EVPN and VPLS interworking as well. Like I said, almost nobody's building brand new networks today. We have to find ways to interconnect those legacy networks into what we're building with this, with the hope that eventually you get to what's on the right, which is the highly optimized network that we're trying to get folks to right now. But that was my last slide. You can find more information. There's that link at Cisco, or even like segmentrouting.net. There's also another website called evpn.io that has all of the EVPN information on it. These are a few other sessions that are going on. I think this one actually already happened. But like I said, this is a good one with Giri. It's another, I think, 2-hour session, but it's everything you've ever wanted to know about EVPN and more. And then obviously they're doing also an EVPN hands-on lab as well. I don't know if those are full or not, but definitely check them out if you want to know more about EVPN. Obviously there's surveys. Fill out your survey. I'm not going to bribe you guys with anything, but thank you.